be talking about how we can model changing amplitude and midline. Because oftentimes within mathematics, just using regular sine, cosine, tangent, cotangent, while those are great, don't always represent exactly what we're trying to represent. Sometimes we might need to change the midline, and remember that the midline is the average. Sometimes we might need to change the amplitude on what our graph particularly looks like. So we're going to start off with an application problem, and we're definitely going to bring in Desmos into this to help us graph to see that changing midline and or changing amplitude that we're talking about. But I do find that it's important to look at an example first to kind of get our bearings about what this looks like and what it might mean. Then we'll graph it. So a population of elk currently averages 2,000 elk, and that average has been growing by 4% each year. Due to seasonal fluctuation, the population is oscillating from 50 below average in the winter to 50 above average in the summer. So there's a couple key pieces within this particular statement. And then finally, find a function that models the number of elk after T years starting in the winter time. So knowing that in the winter we have less and in the summer we have more. So what that might look like. So we're on average growing. So average is letting us know that we're talking about the midline. What is the average that we're doing? And it's growing by 4% each year. So that's going to be a key piece to the problem. And it's oscillating. Oscillating is telling us that we're probably going to be utilizing sine or cosine in this piece here. We have exponential growth. And that exponential growth is starting at 2,000, growing 4% each year. Well, thinking about what exponential growth looks like, our average will be equal to the initial amount that we have, and our initial population we know is 2,000, times 1 plus the rate to the power of time. So in this particular instance, we have 2,000 is our initial population, times 1 plus our rate of 4% to the power of time. We don't know how long, it just says after T particular years. We also know that our amplitude is 50. And I know it's 50 because we go 50 above and 50 below the average in the winter and in the summer. Our cycle is 1 year for our period because our population cycles is 1 year, and that's going to be our period. We also know that when I'm actually finding a particular sine or cosine equation, I don't just need the period, I need the b. Remember, and b is equal to 2 pi, since we're probably going to be using sine or cosine here, 2 pi divided by the period, and in our case we have 2 pi divided by 1 year, so 2 pi. Thinking about what the graph of this might look like, our year in January starts off in winter. So we're going to start off at a particular low point. Then we're going to get high in the summer and come back down, etc. Right? So I'm going to put low in the winter. And this isn't exactly the graph, but just kind of getting an idea of the particular shape. And we are high in the summer. Because of the shape of this, I know I have a negative cosine shape, since cosine typically would start up and we'd come back down. So it's flipped. recalling back to how we write equations, we have P of t, so our population with respect to time. Population is fluctuating up and down. Our amplitude we know is 50 because whatever our midline is, we are 50 above and 50 below that average. So negative 50 cosine times 2 pi times time plus our midline. We're going to put midline for now because we found our average to be this. This is our midline. So this is different than in previous equations. So this is actually going to be the midline. So our midline is actually an exponential equation, and it's exponentially changing. So I'm going to say this is the same as negative 50 times cosine of 2 pi. So our b value times our function of t plus 2,000 times 1 plus 0.04 to the power of t. So this whole midline, again, is the exponential changing midline. Let's see what this might look like if we graphed it. So on the next slide, I actually have the graph of this utilizing Desmos to help us. So notice that our graph is exponentially, the average here in between our ups and downs is exponentially growing. We can have a variety of different types of midlines. So notice that we could have sine of our amplitude times sine of b times t plus a function off to the right-hand side when we're looking at the oscillation. And this is the same thing for cosine as well. So it just doesn't need to be sine, it could be cosine as well. Notice that we have a linear midline. So it's going up into the right, or it could go down into the right as well. So we would write this particular function as f of t is equal to a, the amplitude times sine of b of t plus mt plus b. And notice I'm not putting x, I'm putting t because we are with a function with respect to time in this particular instance. So our variable here is t, but notice that what I'm adding to the end is a linear function mx plus b. We also could have a exponential midline just like the one we had, where we have f of t is a times sine again of bt, except this time I'm going to add an exponential parent function here, so a times b of to the power of t. And finally, we also could have a quadratic midline, where it has the midline is in that shape of a parabola. So this one might look like f of t is equal to a times sine of b of t plus the parent function at squared or ax squared, right? We know that a quadratic function could have a binomial or trinomial, etc. So we're adding on a quadratic to the end. We could add an exponential to the end, or we could have a nice linear line at the end. So let's head over to slide 3, where we can take a look at an example. So find a function with a linear midline. So it's telling us that we do in fact have a linear midline. So we know in this particular instance, our midline is going to be, it gives us the form here. And notice that it's already giving us some key information. So we're just going to have to find the amplitude. It's already telling us the period and things here, or the b value, I should say. But what can we gather from that? We're going to be able to gather a new period here. So if I were to graph this picture, just to kind of get a feel for what it looks like, we have 0, 5. I also have 1, 10, so that might be way up here. I also have 2, 9. And 3, 8. So something that looks like this. All right, so our new period, we have to find what that might be, is equal to the original, which we know is 2 pi, over what our b value is, and it gives us our b value of pi over 2. So our period is 4 units. We know then that the beginning of the cycle is when t is 0, so the point 0, 5. We also know, based on what our period is, that half of 4 would be 2. So half of the cycle is when time is 2, and we know that that point is 2, 9. We can utilize these points to find the midline. Well, in order to find the midline, we need a slope. So the slope of this line, 9 minus 5 over 2 minus 0, 4 halves or 2. And we also know the y-intercept. So our midline, its equation must be our slope of 2 times time, since it tells us that we are in t for our variable, plus the y-intercept of 5. Well, the only thing we're not quite sure of is what the amplitude is, how far above and below, but we do know some information that we can solve for A. I know that we have another point, 110, we can utilize. So if I substitute 10 in here and 1 in for t, I could solve for A pretty easily. So I'm going to start out with my generic function. So f of t is equal to a times sine of pi over 2 times t plus the midline of 2t plus 5. And then utilizing one of the points, let's use 110. So I know the point 110. So I know when t is 1, f of t, or f of 1 has to be 10. So 10 is equal to a times sine of pi over 2 times 1 plus 2 times 1 plus 5. Well, pi over 2 times 1 is pi over 2, and sine of pi over 2, looking at our unit circle, is 1 itself. And 2 plus 5 over here would be 7. So I have a times 1 plus 7 is 10. Therefore, 3 is equal to A. Well, now that I have all of the pieces I need to write the particular equation, I can say that f with respect to t is our A value of 3 times sine of pi over 2 times t plus our linear midline 2t plus 5. So really working all of the different angles that we have with this particular example. Heading over to slide 4, we can put this into the calculator and actually see this in action based on what we found. So we found that our midline was linear. So we definitely can see that our graph is going up in a nice, neat, straight line pattern. I also put the points on using Desmos too, so that I could see that, yes, in fact, my graph is crossing all of these particular points. I can also put in my midline itself. I know that the midline, it crosses at 0, 5, and its slope is up 2 over 1, And I can definitely see that my graph is going up and down this particular line. If I were able to draw straight, pretty clearly, right? Pretty clearly it goes up and down, hovers above and below that midline. All right, the number of tourists visiting a ski and hiking resort averages 4,000 people annually, and here we are oscillating seasonally. 1,000 above and 1,000 below the average. Due to a marketing campaign, the average number of tourists has been increasing 200 per year. Write an equation for the number of tourists, and this one gives us a particular graph to go along with this, which is a nice feature here. Since it's we're starting beginning at the peak of the season, so we're beginning at the peak of the season. So notice on the graph itself that we're starting at 5,000 because it's we're averaging 4,000 to start with, so we're 4,000 above, 1,000 above and below the average of 4,000. So it should make sense that 4,000 would be the midline starting point, but yet 5,000 is the highest point because we are peaking at this 1,000 above the average. So what do we know? We're oscillating is seasonal. This will give me my B value, right? Because our B value is 2 pi divided by the period, and our period is 1 year, right? So every year the seasons filter through. So therefore we know, just like the last example, our period is 1 year, so our B value is still 2 pi. Notice that we're having an average of 4,000 plus we are oscillating or increasing 200 per year. So my average definitely is going to be utilizing a linear line, right? Because we're starting at 4,000 people, but then we're adding, because of this marketing campaign, 200 additional people per year. I also know my A value, my amplitude is 1,000. It tells me that we're going above and below this oscillation 1,000 every time the season is changing. Because we're starting at the peak of the season, we're definitely going to be utilizing a cosine function because we're starting at the peak of the season. Versus the last one, we were starting at the bottom of the season, and because we were at the bottom, we used a negative cosine. It was a flipped cosine. So we have all the parts that we need. We have our midline. We have our amplitude, and we know that we're in a cosine function. Therefore, let's do N of t. The number of tourists with respect to time is equal to our amplitude times cosine of 2 pi t. Since 2 pi was our B value, plus our midline of 4,000 plus 200 t. So this whole piece is the midline. In this particular piece, it's asking us that if we are given this particular function, x squared minus 1 plus 8 cosine of x, describe the midline and amplitude utilizing words. So this isn't really in the manner in which we have been writing items, so our cosine should probably come first. So all I'm going to do is rewrite this so that g of x is equal to 8 times cosine of x plus the x squared minus 1 portion. Notice my midline is quadratic, so we have a quadratic midline. And based on that midline, we know that our amplitude is constant, 8 above and 8 below that quadratic midline. But we don't always want to change our midline. What if we want to change the amplitude? What if I want to change the amplitude? So notice the pictures. I've got a linear amplitude, an exponential amplitude, and a quadratic amplitude. These are pretty interesting in and of themselves. So if I have the amplitude that's changing, I'm now going to put a function as my amplitude. So my function of my amplitude comes first, and it will oscillate above and below the amplitude, the midline, with a specific amplitude itself. So this first one, this linear amplitude, our graph function would have f of t equal to a linear parent function, so m of t plus b, so mx plus b or m of t plus b, times sine of capital B of t plus a midline. And yes, in fact, you can have a function for your midline and your amplitude at the same time. We're just kind of working on one or the other right now. Similarly, if I want to have an exponential amplitude, I will have f of t equal to an exponential parent function, a times b to the power of t, times sine, and it could be cosine, of b of t plus our midline. And finally, we can have a quadratic amplitude. So f of t is equal to a of t to the power of 2, since it'd be ax squared, the parent function, times sine of b of t plus k. On the next page, we also have something that's called a damped harmonic motion. This is exhibited by springs subject to friction, and it follows the following model. So notice it's starting up above, and it's really high and up and down below, and then all of a sudden it kind of levels out. And these functions can be found by taking ab to the power of t, so the exponential amplitude, or it could have a e, so base of e to the power of the rate times the time of sine of b of t plus k. So pretty interesting different pieces here. So I've got an example off to the right-hand side, example 5, and notice I do have its picture so we can see what it looks like after we build it together. So a spring with a natural length of 20 feet is pulled back 6 feet and then it's released. It oscillates once every 2 seconds. Its amplitude is now decreased by 20% each second. Find a function that models the position of the spring t seconds after being released. So we definitely know that our midline is 20 feet because it tells us. So we're going to go above and below that natural length. We also know that it's oscillating once every 2 seconds. So its oscillation seconds, we'll just say that. So our B value can be found, it's either going to be sine or cosine, so 2 pi divided by those 2 seconds. The period is 2 seconds, so it goes through one cycle every 2 seconds, is equal to pi. Since we are starting the furthest from the wall to start with, we're going to use a cosine model. Since we're starting the furthest away from the wall. Our amplitude then, it's going to shrink. It says that the amplitude is decreased by 20 seconds. So our initial length away from the wall is 6 feet. And then we are subtracting 20% to the power of time. So notice this is now going to be our new amplitude. It's a function, an exponential function at that. And so our overall function is f of t, so the distance away from the wall with respect to time is 6 times, I can simplify in here, which is 8/10 to the power of t. We already decided cosine. Our b value is pi times time plus the midline of 20. And then off to the left-hand side, I do have the graph listed there. We can definitely see, of course, we don't care what's happening to the left of the left here of the y-axis because time can't be 0. So as time starts, notice we started the furthest away from the wall, and then we oscillated, and then it lost every second. It loses its amplitude is decreasing. Let's do another example similar to this. And I also have the graph listed here. A spring with a natural length of 30 centimeters is pulled out 10 centimeters and released. It oscillates 4 times per second. After 2 seconds, the amplitude has decreased to 5 centimeters. So we're going to have to find out what that exponential decrease is. Find a function that models the position of this particular spring. So we are given the midline, the length of the string itself. Which is 30 centimeters. We also know that it's oscillating one-fourth of a second because it is doing 4 times per second. So we are oscillating 1/4 of the way per second. I can find our b value by saying 2 pi divided by 1/4. So 8 pi is our b. Since we're starting at the furthest length away from the wall or wherever we're hooked up to, we're going to use the cosine model. Since we're pulling out our string and we are the furthest from the start, if you will. So right now what I have is our function with respect to time is equal to whatever our amplitude is. We're going to have to discover that times cosine of 8 pi t plus 30. There are a couple of other things that I do know. I do know that when time is 0, we are we are 10 centimeters away, our length is. I also know that after 2 seconds, we are now at 5 centimeters because it tells us after 2 seconds, we are at 5 centimeters. So 0 represents time, and this t represents the distance away, so a of t. Oh, we shouldn't put a of t. I should put f of t on both of them. I do know that we are going to be exponentially based on the type of problem because it says that it's coming and then it's decreasing over time. So therefore, a of t has to be equal to ab to the power of t. Well, I know initially that we are at 10. I also know that when we are a certain amount of time away, so when time is 2, we're now at 5. So we can go ahead and solve this utilizing our initial rate, our initial length. So this was our initial length, and using what we do know so that we can find what b is equal to. So right now I've got half is equal to b squared. And if I take the square root of 1/2, it's going to be a pretty ugly number. So b is approximately 0.707. Pretty ugly decimal, but it works. Therefore, a of t is equal to 10 times our base of 0.707 to the power of t. Now that we know what our amplitude is, we can find the final function. F of t is equal to 10 times 0.707 to the power of t times cosine of 8 pi t plus 30. And then, of course, I've got the graph listed there so that we could see it in action. On slide 9, a certain stock started at a high value. So I'm going to stop there. Since it started at a high value, we know that we're going to be working with cosine of $7 per share, and it's oscillating monthly above and below the average value. So it's oscillating monthly. That might be important. Above and below the average value, with the oscillation decreasing by 2% per year. However, the average value started at $4 per share. So the average value started at $4 per share. This is linear. And has grown, and then it says linearly, by 50 cents per year. Very interesting. So find a formula for the midline and the amplitude, and find a function S of t that models the value of the stock after t years. We've got a couple of different things happening here. We have our midline. We know that we started at $4 per share, and that to that we're adding 50 cents per year. But it's oscillating above and below this average, telling us that it's oscillating above and below, decreasing by a exponential function itself. So our amplitude is a little different. Our amplitude, original starting value, it says it's 7, so our initial starting value is 7, times 1 minus 0.02, since it's decreasing per year to the power of t. And this can simplify to 7 times 98 hundredths to the power of t. We're doing this monthly, so every month it's oscillating. Therefore, b is equal to 2 pi divided by 1/12, or 24 pi. This gives us then a function for our midline and a function for the amplitude. The stock value is equal to our amplitude of 7 times 98 hundredths to the power of t. Since we're starting at the high value, we said we were going to use cosine of 24 pi t plus our linear midline of 4 plus 0.5, 50 cents per share. So we have a linear and we have an exponential amplitude and a linear midline. And we can definitely see that when I graph, we can see what's happening at both of these instances, with respect to time and years, of course. All right, our last example. In AM, which is amplitude modulated radio, a carrier wave with a high frequency is used to transmit music or other signals by applying the to be transmitted signal as the amplitude of the carrier signal. So of the amplitude of the signal, A musical note with a frequency of 110 hertz, when hertz is cycles per second, is to be carried on a wavelength, of a wave with frequency of 2 kilohertz, which is thousands of cycles per second. If the musical wave has an amplitude of 3, write a function describing this broadcast wave. All right, so some of the things that we know are 2 kilohertz. This is equal to 2,000 cycles per second. This tells me that the period is 1/2000th of a second. I know then that B has to be equal to 2 pi, since we'll either be using sine or cosine here, over 1/2000th of a second, or 4,000 pi. So right now I know that I have sine or cosine, because it doesn't tell us if we're starting below or above. So we'll just use sine or cosine. We haven't used sine, so I'll use sine this time, of 4,000 pi t. All right. The musical tone is acting like an amplitude. At 110 cycles per second. So in this instance, P is equal to 1/110 of a second. So our B value is 2 pi divided by 1/110th, or 220 pi. And it tells us that the amplitude of this particular piece is 3 with the musical tone. So therefore, the musical tones equation is 3 times sine of 220 pi t. So wait a second. This is the amplitude of the carrier signal. So this whole entire portion represents the carrier signal. And this whole section represents the amplitude of that carrier signal. So we know that the word of in math means to multiply. So I've got a sine function as the amplitude function of the carrier signal. So then all together, our function with respect to time is 3 times sine of 220 pi t times sine of 4,000 pi t, and we don't have any midline. It doesn't tell us a midline. So we have an amplitude that is in fact a sine function, whereas we've only talked about quadratics, we talked about linear, or we talked about exponential, but they definitely could have sine functions or any function, any parent function as the amplitude. So on the last slide then, I've got the picture of what this might look like. Noticing that our amplitude is in fact going at a wavelength up and down, that we can see kind of something like this. Well, not exactly like that, but you can kind of see that it is hovering up and down. That amplitude is going up and down, just like a sine function goes up and down and then repeats itself. So pretty interesting that we can have a sine function or any function, any parent function, as our amplitude. And that concludes all of our lessons for Unit 7.